Hey everybody, today we're going to talk a little bit about polarity and electronegativity. Essentially, we're going to talk about how electronegativity plays a role in what types of bonds are going to form between atoms, and then how that's going to change how electrons are shared within the molecule that's formed. So first let's talk about what a polar covalent compound is. What is polar covalent bonding? So we know what covalent bonding is. We know that that's the sharing of electrons between atoms in a chemical bond. But polar is a new word. This is a new addition for us. But what I mean by polar, this is when we have a covalent bond in which electrons are not shared equally. So there is sharing that's happening, but one atom is kind of hogging the electrons towards itself. Essentially, that's going to look like this down here. So here I have oxygen and bonding with two hydrogens. And essentially what's happening is oxygen is kind of being an electron hog. So oxygen is hogging those electrons over here. So we get this partial negative. So we see kind of this, that means partial negative. So we see this partial negativity happening on this side of my molecule because my negatively charged electrons are being gathered more over in this area. Whereas with our hydrogens over here, they don't have possession of those electrons quite as tightly because oxygen's kind of hogging them. So over here, there's fewer negatively charged electrons hanging out. So we're going to see these partial positives over in these areas. So they're shown here. So because the nucleus of these hydrogens is kind of exposed a little bit more, we see kind of this partial positive side. So this side of my molecule is a little bit positively charged. So we see slightly negative over here and slightly positive over on this side. So that's what it means to be polar covalent. When we look at the periodic table, what determines whether a molecule will be polar or nonpolar is based on the electronegativity. So we've talked about this already, and we talked about it with our periodic trends. So this is the relative ability of an atom to attract shared electrons to itself when it's bonded. So remember, this is the attractiveness of an atom. So atoms in the upper right, so over here fluorine, are going to be my more attractive. And then down in the far bottom left, they're going to be my least attractive. So in general, we see an increase as we go from the left to the right across the periodic table, and we see a decrease as we go down. So we've talked about this trend. We, in general, see an increase in electronegativity as we go up and to the right on the periodic table with electronegativity. And these values are going to be really, really important, and we'll talk about it in a minute. I will always give you this electronegativity chart from now on, so you'll always be able to actually see the real values of electronegativity. So here you can see that the electronegativity of beryllium is 1.6, but sodium is 0.9. So beryllium has a higher electronegativity than sodium, which means beryllium is going to attract electrons when it's bonded more closely to itself than sodium is. So now let's just practice identifying which atoms are more electronegative. So let's look at oxygen versus sulfur. So here's my oxygen, here's my sulfur. Oxygen has a greater value. It's also higher on the periodic table. And remember, we see an increase up and to the right. So oxygen is going to be more electronegative. Which atom is more electronegative, chlorine or carbon? So let's find them. Here's chlorine and here's carbon. Chlorine is farther to the right. Even though it's down a row, it's over 4 rows, so we do see an increase in electronegativity. Chlorine has an electronegativity of 3.0, whereas carbon has 2.5, so chlorine has a greater electronegativity. Now let's look at selenium versus arsenic. So here is arsenic. Selenium is right next to it, right here. So selenium, it's farther to the right, so that should indicate to us that it should have a higher electronegativity, and we see that it actually does, 2.6 versus 2.0, so selenium is more electronegative. All right, so the polarity of the bonds depends on the difference between the electronegativity values of the atoms in the bond. So now we're going to be looking at what is the difference in electronegativity within these bonds. If the difference is really big versus whether it's really small, it's going to indicate to us whether it's going to be polar or nonpolar or even ionic, where there's no sharing that's happening at all. Okay, So we're going to see a non-polar covalent bond if the difference between the electronegativities is 0, or really we're looking at between 0 and 0.4. So 0 to 0.4, we see non-polar covalent compounds. So that would be, so here if I have two hydrogens bonded together, each one of those hydrogens has an electronegativity value of 2.1. So the difference between 2.1 and 2.1 is 0. So I know this is going to be a non-polar covalent compound, which means that these electrons between those hydrogen atoms are going to be shared equally between the two hydrogens. So I now, if I look at my polar covalent, so here we're going to see a medium electronegativity difference. Really, we're looking at between like 0.4 to 2 or so is going to be my range for polar covalent. So here if I look at hydrogen bonding with fluorine, hydrogen has an electronegativity of 2.1. Fluorine has an electronegativity of 4.0. So the difference there is 1.9. So what that tells me is that fluorine is going to attract the electrons more tightly than hydrogen is able to. So these electrons are going to be hogged over here on the fluorine side, which means I'm going to have a partially negative end with the fluorine and then a partially positive end with my hydrogen, and that will make this a polar covalent bond. Sometimes we can have such a large difference in electronegativity that electrons don't end up being shared at all. And this is where we see the introduction of these ionic bonds. We're going to talk more about these in our next unit, but this is when we have a really large electronegativity difference. So here I have lithium bonding with fluorine. Lithium has an electronegativity of 1.0, which is fairly low, and fluorine has an electronegativity of 4.0. So there we have a difference of 3. So pretty much here, large differences, that's going to be anything greater than 2.0. So in this case, fluorine isn't even going to share its electrons with lithium in this particular situation. So instead of sharing, lithium is just going to lose its electrons entirely to fluorine when they bond. So we're going to see the total transfer of electrons, which is going to create an ionic bond instead of a covalent bond. All right, guys. So go ahead and take a look at the website, do your notebook problems, practice identifying when compounds are going to be non-polar covalent versus polar covalent versus ionic, and then you can watch the videos of me going through those problems below. If you have any questions, go ahead and leave them at the end of the video for me. See you guys tomorrow.